everyone, this is Alex, and welcome to video number 3 of our little proof series. So in this video, we're going to be discussing another common method of proof, which is proof by contradiction, or if you want to be fancy, as you can see from the title here, Reductio ad Absurdum, which is the Latin for reducing to absurdity. And that kind of gives us a clue as to what we're supposed to generally be doing in these kinds of proofs. So in other words, if you want to show something's true, well, what if you assume it's false instead, and then show that logically leads to some conclusion that's obviously false or impossible? Well, that's exactly the kind of proof that often carries us through a lot of exercises or really cool statements, whether they're routine or more extravagant. So, for example, here's a more common use of proof by contradiction. Let's say we wanted to prove that the square root of 2 was irrational. First, let's recall what it means for a real number to be irrational. That means it can't be written. Let's write this down. Irrational, as in can't be written in the form p over q, where p and q are positive integers. But this is important, not just any positive integers. They have to be positive integers with a common factor of 1, with the greatest common factor of 1, I should say. Greatest common factor. So in other words, we have a term for this. We call them relatively prime. So for example, 7 and 12 are relatively prime, but not 4 and 8, right? Because 4 and 8 are both divisible by 4, but 7 and 12 aren't both divisible by any of the same thing except for 1. So, that relatively prime part's key. You can't have a representation of a half as, say, 2/4 or 3/6. Those don't count as rational numbers. You can just reduce them to a half. A half would be the rational number. So how can you show that a square root 2 can't be written in that form? Well, let's say we could. Let's go on to the next slide. Let's pretend we could. We're going to assume square root 2 is p over q, where this, again, the important part is that GCD of p and q is equal to 1, right? So what's a natural first step? Well, the first thing we want to try and do, just instinctively, out of habit, right, is get rid of the square of roots. Nobody likes square roots, right? So you just square both sides. You get 2 equals p squared over q squared. You multiply both sides by q squared. You get 2q squared equals p squared. So great. Now what? That left-hand side is twice some perfect square q squared, right? Well, it's definitely an even number, so that's for sure. So left-hand side. And by the way, I'm going to refer to this like common abbreviation for left-hand side as LHS, and similarly RHS is right-hand side. So LHS is even. That means the right-hand side also has to be even. In other words, p squared also has to be an even number, right? So what that tells us is that actually p is even because of, you can refer back to video 1 where we showed that the square of an even number is always even and the square of an odd number is always odd. So that means p has to be even, right? So if p is even, that means p can be written in the form 2k for some integer k, right? That's what it means to be an even number. That means p squared would be 4k squared. If 2q squared is equal to 4k squared, what does that make q squared equal to? Well, that makes it equal to 2k squared. But again, that means q squared is also an even number, which means q is even. So we have our contradiction, right? Because, right, if we go back to the definition of a rational number, what's that telling us? Well, it's not up here, but it's telling us that p and q have to be relatively prime. This part especially is key, right? Because we've just shown that p and q are both even, and what that really means is that they have a common factor of 2. The greatest common factor is at least 2. We know 2 definitely divides both of them because they're both even, but that can't happen because that's not the definition of a rational number. So that means square root 2 can't be rational. Therefore, it must be irrational. So that's a fairly classic example of contradiction. But for this video, we're going to present a second example to really solidify the idea. Right. So here's a sketch of what we just did. Right. Maybe I should leave that up there for a little bit while I introduce my next example. The next example is going to be something that's actually super important in the field of real analysis. And if you're interested in the more formal name for this result, it's called the density of the real numbers, as in, I guess in loose terms, between any two given real numbers, there always exists a third real number in between them. And we can use this to show, for example, that there's no least positive rational number, right? Give me any small positive rational number you can think of, like 1/10. Well, 1/20th is what I give you back as in response to that, right? A smaller rational number that's still positive. You say 1/100. Well, how about 1/200? 1/1,000,000, 1/2,000,000. And I think you can see where this is going, right? What are we trying to contradict here? We're trying to contradict that there is a smallest positive rational number. Call it R. Assume there is a smallest positive rational number R. Well, we want to contradict this. We want to show this leads to some nonsense conclusion, right? Now, what number can we come up with that's smaller than R but still greater than 0 and still rational? Well, why not just divide it by 2? Right? R/2 is always going to be between 0 and R, right? Because as I was alluding to with my examples, right? I chose 1/200 for 1/100 and 1/2,000,000 for 1/1,000,000. It doesn't have to be division by 2. It could be division by 10 or division by 100 or even division by a billion. It could be like really it could be just anything, right? That's less than R and still positive. So we've just found our contradiction. And even though this was a shorter example, it's arguably an even more beautiful one, right? Because it just paves the way for the whole field of analysis, really. I mean, the other ones, the square root 2 is irrational, I guess, is kind of similarly beautiful because it also paves the way for like let's say number theory, and how this kind of led to the whole Pythagoras, the Pythagorean theorem construction, right? Like 1 and square root 2, showing that you can't like square the circle and that sort of thing. So I'd say they're pretty much both equally beautiful examples. If you're interested in even cooler arguments, I'd highly recommend looking up Cantor's diagonal arguments, which actually gives rise to a proof that the set of all natural numbers or positive integers, right, is not the same size as this set, right? 1, 2, 3, so on, is not the same size as the set of all real numbers. I mean, surely you're thinking they've got to both be infinite, right? Well, yeah, I mean, it wouldn't be wrong to say they're both infinite size, but set theorists aren't really interested in just leaving it at that, just saying, oh, it's infinite, right? They're much more interested in what type of infinites these sets are, right? Can two sets be directly compared to each other with a bijection, for example? We want to know if there's bijection means same cardinality. Do they have the same infinite size? Are they equally infinite? Or are some infinities bigger than others? Well, yes, it turns out there's plenty of infinities that are bigger than others. There's a whole hierarchy of sizes of infinity, so to speak. And if you're interested in set theory, you can look that up with like cardinal numbers and ordinal numbers and like Aleph null and that sort of thing. Aleph null, by the way, is what's called the cardinality of the natural numbers, right? And any set that's bigger than that set, any set that has a cardinality bigger than Aleph null is considered to be uncountable, where the natural numbers are countable because, well, you're counting them 1, 2, 3, 4, 5, but you can't do that with a set that's bigger than that can't be put in bijection with the natural. So anyway, I'm just going off on a bit of a tangent, I guess. Again, if you're interested, you can check that out. But for now, here's a few exercises, which again, I'm going to leave in the description. Some of these are classical, I guess. But there's a bit more, there's a bit more interesting one at the bottom here, exercise 3. But that's, again, I'm going to leave that in the description. But for now, that's the end of this video, and I look forward to seeing you around next time. Take care. Have a good one.